on this computer. All right. What we're going to do to start with is I'm going to talk a little bit about algorithms, and then we're going to actually do some programming together. So let me go back to my slides. I think that's it. Share. I don't think I'm sharing the right thing. Okay, let me stop. Try again. Sorry. Well, that's weird. I don't see the usual. Are you guys seeing the slides? Introduction to algorithms?
Yeah.
Yes.
Okay.
Yeah.
Huh. Normally it highlights it and it doesn't seem to be working. All right. Well, as long as you're seeing that, then I'll continue on. Okay. So let's talk a little bit about computer science and algorithms. So at its most fundamental basis, computer science is actually the study of algorithms, okay, including their formal and mathematical principles, how they're realized as actual hardware systems, how they're defined in terms of languages, and then how we take and build those into useful applications. What is an algorithm? Now, some of you may have heard the term algorithm before, and if you have, that's great, but some of you may not have, okay? So what is an algorithm? Well, at its simplest point, an algorithm is basically a set of instructions for how to solve a problem. And in fact, it's an ordered sequence of instructions that is guaranteed to solve a specific problem. So an algorithm is a specific solution to a specific problem as a set of ordered steps. For example, we can think of it as you have a step and you do something, and then when you're done with that, you have step 2, which you do something else, then you do something else, and you keep doing things until you're done, right? Now that seems pretty simple so far, but now the thing is when we're talking about algorithm, we got to talk about what does this do something part mean? Well, we could think about an algorithm in real life, like an algorithm for how to change your tire if you get a flat, right? And so you could say, well, step 1 is you get out of the car. Step 2, you walk around the car to see which tire is flat. Step 3, you open the trunk up. Step 4, you take out the jack. And step 5, you put it under the car. Step 6, you start to jack the car or usually you turn the thing and say you turn it. Is the wheel off the ground? No, you turn it some more. Is the wheel off the ground? You turn it some more. And so on. We can talk about an algorithm for changing your tire. Now, the steps are things that we physically do. But when we're talking about a computer, sorry, I need to jump ahead. I guess I did. When we're talking about a computer, the steps that we do are the operations inside of a computer. And it turns out that a computer can only actually do a few operations, but by doing lots and lots of simple things, it can do everything from Google searches to allow you to play video games, right? And so what all of this is based on is simple operations that are being performed by the computers as a series of steps, just like we talked about. Now, it turns out that we can organize our steps 3 ways. And in fact, we use combinations of these 3 ways to build an algorithm. One is a sequence, which we just saw. We do one thing, then we do something else, then we do something else, then we do something else. We have sets of instructions like this all the time in real life, and this is generally what computers do. But there's a second type of thing. One thing that makes computers smart is they can look at some information and decide what to do next. That's called a conditional operation. So generally, computers can make a decision. And generally, a decision is a yes or no question, a true or false. Is this true? If it's true, we do this. If it's not true, we do that. And so that's a conditional. So in addition to sequential operations, we oftentimes have a situation where we decide based on some information which of two options we take. And then the third thing is iteration. We saw that with the tire, right? We turn the crank, we look and see if the tire is off the ground. If not, we turn the crank, we look and see if the tire is off the ground. We turn the crank, and when the tire is off the ground, then we're done, right? So generally speaking, when we have iteration, there's an underlying assumption that the task that we're doing is going to eventually lead the condition that we're basing the information on to no longer be true, because we could say the jacking up process is something like, is the tire off the ground? No, while the tire is not off the ground, crank. It's 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 off the ground, we don't crank anymore, right? So that's the notion of looping or iteration. And so again, we have sequence, we do things step by step by step. We have conditions where we pick between multiple things. That's sometimes also called selection. We select an option. And we have iteration, which we do things over and over again, which is also called looping. So here's pictures of these three things. Sequence, we do something, it leads to another thing, it leads to another thing. Selection, we have a choice, we have a condition that we check, right? Is this variable greater than 3, right? Is the car off the ground? If it's true, we go one direction. If it's false, we go the other direction. So we ask a true or false question, and that makes us take one path or the other path. And then the third thing is looping. And looping, again, is we have a choice like we did with selection, but instead this choice causes us to do an instruction and check, do an instruction and check, do an instruction and check. And as long as it is true, we keep doing it, and when it's no longer true, we stop. Okay, so it turns out that these are fundamental to all algorithms. In fact, these are all we need in terms of controlling a sequence of operations. This is it. We can come up with more things, but they all boil down to this. In fact, nobody's ever found anything that gives us more capability in writing an algorithm than these three things already provide. So here's an algorithm. You might have a DVR, right? And you hook it up to your cable or whatever, and you want to program it to record shows at certain times, right? Now, this is less and less a thing of it's more and more a thing of the past, quite frankly, because everybody just streams things on demand now. But sometimes if you watch cable, right, you have a show that you can't see, and you want to program the recorder to record it. Well, so here's a program, an algorithm, right? Step 1, you set the clock and the calendar. Step 2, you repeat steps 3 through 6, as long as there's another program you want to program in. And then 3 through 6 is the process of you entering in the information necessary, the channel, the start time, and the end time. And you can repeat those. And then you turn off your DVR and let it record the shows at those particular times. So that's an algorithm. Now, actually, I'm going to skip that one. So now the thing about algorithms is they are central to computer science. In fact, if we can specify a well-defined algorithm, in fact, by definition, an algorithm is well-defined to solve a problem, then we can automate its solution, right? In fact, a lot of times when people say, well, I couldn't write a program to do this, what they're really saying is I couldn't figure out what the algorithm was in order to do it, right? So you have to know how to do something before you can write an algorithm to do it. Now, in the world of computing, not only do you need to have an algorithm, but then you need to have something to execute the steps of the algorithm, right? Could be your computer, could be a machine, could be a person, something to carry out the steps. So we can write algorithms that solve problems. What is a problem? Well, a problem is anything that we might want to do. Now, what's interesting about computation is, and even about algorithms in general, is we actually can't solve all problems. We can come up with lots and lots of problems. In fact, an infinite number of problems that we can solve. And we can also come up with an infinite number of problems that computers can't solve. And so computers can't do everything. And when I say they can't solve them, there's two reasons they can't solve them. One reason is because it's not something that a computer can do. A computer just lacks the ability to do it. The other reason is because it would take so long to do it that it's not useful, right? If it takes 1 billion years to solve a problem on a particular computer, and that's the fastest computer you have, well, sure, we can start the program running, but it's not going to do us any good, right? And there's actually lots and lots of programs like that, and lots and lots of algorithms like that take too much time. So here's the formal definition of an algorithm now. An algorithm is a well-ordered collection of unambiguous and effectively computable operations that, when executed, produces a result, the result you want, and halts in a finite amount of time. Now, let's look at what these pieces mean. Well-ordered collection. So a well-ordered collection, upon completion of an operation, we always know which one to do next, right? If you don't know what order to do things in, then you got a problem. Well, if we go back for a second, that's all about sequence selection and looping. That's what helps us know the order in which we do things. The second thing is that it must be unambiguous and effectively computable operations. So it's not enough that an operation be understandable, it must be doable, effectively computable, right? You know, if you actually have to have a machine or a thing or a person that actually knows how to do that step, right? And so if we're talking about changing a wheel, it's not effectively computable, for example, if you don't know how to remove the lug nuts. If that's not something the person doing it is capable of doing for whatever reason, then it's not doable, right? So you have to, it has to be something that can be done by the machine or person that needs to be able to do it. It also needs to be unambiguous, right? In real life, there's lots and lots of things, as we talked about the other day, that are ambiguous. But for an algorithm, you can't ever be any doubt about what exactly it's supposed to do. So things like go back and do it again is ambiguous because we don't necessarily know what it refers to. Start over. What does that mean? Where do you want to start over? Start over the whole thing, start over something that we, a subpart, right? We need things to be absolutely, completely defined. So then the next part of an algorithm is that it produces a result and halts. Well, that's weird. What just happened? Did it go blank for you guys?
Yeah.
Yes.
Yep.
Never seen that before. My whole, all right, let me clear that and start another one. It's not a big issue, hopefully. Fortunately, I have lots of redundancy here. Okay, so we're going to try again. There we go. That's not what I wanted. Well, I guess I can do that here. All right, you see them now, right? Are the slides back up?
Yeah.
Okay.
Yes.
So, I don't remember where we are at. Oh yeah, produces a result and halts in a finite amount of time. So to know whether a solution is correct, an algorithm must produce a result that is observable to the user. That could be a numerical answer. It could be some new object. It could be a change in the environment, right? So for example, an algorithm to control the thermostat in your house, it's working if it correctly changes the temperature in your house to the desired amount, right? So an algorithm has some sort of inputs, does some processing, and it produces some sort of a result. And it has to do it in a finite amount of time, right? Writing an algorithm that never ends so that it never gets a solution is not, it's not an algorithm even by definition, because an algorithm by definition finishes after a finite amount of time. And it's, by the way, it's easy to write an algorithm that never ends, but they're not of any value. So again, the unambiguous or operation, sometimes we call these primitive operations. And what that means is there's the base operations that a particular machine can perform. So when you say do this, there has to be exactly one thing that the machine will do. So it's not enough that a machine be understandable, though. It has to be doable, right? And so the sort of things that computers do are add or subtract or compare two things, like say, is this number greater than that number, or multiply, or you know, pick a particular step to do. So now, finally, we don't want our algorithms to have infinite loops, usually. Okay, there are some exceptions to that, but they're way beyond what we want to talk about here. In other words, we don't want a program that gets into a loop that it can't get out of. So here's a simple, correct solution for shampooing. Step 1, you wet your hair. Step 2, you set the value of this variable wash count to 0. Step 3, you repeat steps 4 through 6 until wash count equals 2. Well, wash count is currently 0, so we're going to do it. Start it. We lather our hair, we rinse your hair, we add 1 to wash count, and then we go back and we check. Is wash count equal to 2? No. It should be equal to 1 because we started out with it equal to 0 and we only added 1 to it. So we lather our hair again, we rinse our hair again, add 1 to it. Now it's what wash count? It's 2, right? And so we go back up to 3 to check, and we say, oh, wash count's equal to 2, so we're done. And we go to 7 and we stop. We've now washed our hair. So that's an algorithm for shampooing. Now here's a different algorithm. Wet your hair, lather your hair, rinse your hair, lather your hair, rinse your hair, stop. Now, from a practical standpoint, are these, obviously these are slightly different algorithms, but is the result any different at all? Anybody? What do you think?
No.
No, they perform exactly the same steps. It's just a different way of doing it. Oh, somebody asks, are these slides are available on the web page under the slides section. So you have your own copy of these slides and you can do whatever you want to with them. So it turns out for any problem, there's an infinite number of possible algorithms, right? Is one of these algorithms better than the other? Well, you could say that this one's better because it's simpler. You could say that this one's better because you could change this number 2 here to number 3 if you wanted to have one where you wash your hair 3 times, or change it to 1 if you want it to so that it only lathers your hair up once, right? So this one might be a little more flexible, but they both do the same thing as written. So algorithms are huge. Algorithms are so unbelievably huge in mankind. They are probably among the top 5 inventions, or maybe even better than that, ever made by mankind. Because, you know, for one thing, algorithms led to the Industrial Revolution. What happened for the Industrial Revolution? We made factories for mass production, right? And that changed the world, right? When instead of a silversmith making one teapot at a time, they could make a factory that had a set of steps that would go from some, you know, metal to a teapot that could be repeated over and over again in precise steps, and you could make the same exact teapot over and over again. That was huge, right? And that's really just an algorithm, only this algorithm is running on a factory instead of on a laptop. The computer revolution, of course, is what brought us to today, and which has had profound implications. In fact, it turns out that the economies of every country on the planet depends completely on computation, and we certainly couldn't be doing remote classes without computation. And so it's hard to overestimate the value of algorithms, because they are the theoretical foundation of all of this. So that's just sort of an overview to get us started and to get us thinking about algorithms. Now, so if we go back to today, we have this thing, Fun with Candy Bars, and I'm going to open that up. And this is something we're going to look at today. And this is something that you turn in that you're going to be kind of working on with me in class today. And please ask questions, and then you're going to finish it on your own and turn it in before next class, okay? So this is a chance for us to sort of talk about and experience the things we've been learning in our modules over the last couple of weeks, okay? So what I'm doing is and I hope you have made your REPL, have answered the email, not answered, but used the email I sent you to invite you into REPL, because if you haven't, you need to do that. Now this will work without the account, but we're going to be doing things in the future that will require an account. So if I click on this link, which is what you should do too. Oh, I'm sorry, I'm not sharing my screen. Okay, so let me, sometimes I, okay. Okay, so hang on here. I have to, hang on. I have to unpin this thing because it's blocking my, all right, I'll just move this. Okay, so you guys are seeing, okay, so here is the syllabus, and on the syllabus we have this Fun with Candy Bar things, and if you click on that, we see this, okay? And there is a Moodle thing in your homework where you're going to turn in the REPL that you made today. And so what you should do is click on this, and you'll get this, okay? Now this is REPL. We've talked about it a little bit, not a lot. We're going to start learning about it a little bit more now. Here is files within the REPL, although for right now we're only ever going to have one, and I'm going to close that. Here's our program, which contains statements and comments. And then here's where the program output is, input and output is. And in fact, I can run this program and we can see that it will ask us, it says this program allows you to make calculations about your bag of candy bars. What kind of candy bars do you have? So we could type in Snickers, number of candy bars in the package. Let's say we have 12, weight of ounces of one candy bar, let's say 3.1. and it says you have 12 Snicker bars, 3.1 ounces each, and the total weight is 37.2 ounces. Perhaps you should consider a healthier snack. Oh shoot, I actually need to get rid of this because we want to write this. I left some code in. I didn't do what I'm going to tell you to do now. Okay, what I want you to do is do what I do. I want you to re-go to that. Okay, so close the window if you already went there and re-go there. Okay. And then what I want you to do is make your own version. And the way that works in REPL is if you click here, we can say fork, and it makes our own version. It changes the name. And now if you want to make it have your own name, you can, like you could make it, whoops, I don't know what I just did there. I clicked the wrong button. What we can do is if we click down, I can make candy bars, SCMP118 afternoon. You know, I'm just calling it this. You can call it whatever you want. Okay, so now I have it. Now, by the way, once I've made something, if I go over here to my REPLs, I will always see all of the REPLs that I've made. And here's the one we just made. And so you'll be able to go back to this later and turn it in. Is that making sense? Any questions? So basically, this is an environment where you can write programs and you can save programs, and you can get to those programs from any place that you can get to the web. And that's the beauty of this programming environment. Now let me close this down. And if I run it again, this program, what kind of candy bars? Almond Joy. No, I guess I don't know how to spell almond joy in my way. I never can spell when I'm typing in front of people. Enter the number of candy bars in the package. 15, enter the weight, 4.2, and it says total weight is 63 ounces, 15 Almond Joys, 4.2 ounces each. You should consider a healthier snack. So that's a program. Now you guys should all have your version that you can now start to add things to. Now let's look at this program a little bit. This first statement here, first it prints out information about this program. Then it does this. Now what does an input do? I'd like somebody to tell us what an input does.
Isn't an input like basically a piece of code that when someone puts information that it will spit some kind of information back? I mean,
right. Yeah. That's right. And whoops, did not mean to do that. So, like if I say X is equal to input, what happens is the computer waits. It doesn't do anything until I type something in. So if I say 4, now if I type X, X has 4 in it. And I can do that with any variable I want, right? You know, and I can type in Kenyan, and then XYZ is Kenyan. So the thing is input waits for something to be put in. Now, if I do this, I can actually put a string in here, and that's what's called a prompt. That causes the input to put something out to prompt the user for what it's looking for. So I could say, you know, what is your name? And it says, what is your name? And I type in Jim. And now if I look at XYZ, it's Jim. Now, what type of thing does input always get? Does anybody notice in Python, variables have types? And what is the type of the thing? Notice when I typed in a 4, I had 4 in quotes. When I typed in
Right.
Kenyon, I had Kenyon in quotes. When I had Jim in quotes. In fact, if I say type XYZ, whoops, I didn't type in my Z, we see it's an str, a string. And we saw that before. Types, we can have integers, we can have floats, and we can have strings. That's all we know about so far. But what is the type when we do an input? Well, let's find out. Type XYZ, it's a string. Now notice, if I do this, wait, I want to do this one. I'm going to find this one. If I say this, input X, and I type in a 6, we might say, well, now the type of X is going to be an integer, right? Well, let's find out. Nope, it's a string. It turns out that input always takes its input as a string of characters, a thing in quotes. And you can't change that. Now, that's fine for the name of the candy bar because we want the name of the candy bar to be a string. But for the number of candy bars, we don't want a string. We want an actual number because we want to be able to do computations with that. We can't, as we've seen in the modules, we can't do multiplications and adds with a string, right? In other words, I can say 3 plus 4 is 7, but quote 3 plus quote 4 is actually going to take and concatenate 2 strings together. So I get 3, 4. I don't get 7, right? Because I'm just bringing strings together. And in fact, if I try to do this, 5 plus quote 6, it's going to say, yeah, you can't put strings and numbers together. So here, when I ask for the input of a number of candy bars, this does the input because we've already seen that's what an input does. But when I wrap that in int parentheses, it applies what's called a function to that. Remember, we saw that does a conversion. We've seen this before, right? If I say int 4, I just get a 4. If I do int 6.445, I just get a 6, right? If I say int quotes 343, it converts it into an int. It doesn't have the, now of course, if I do int Kenyon, what's going to happen?
It's going to show error.
Right, it shows an error because Kenyon is not able to be turned into an integer. And so it turns out that's actually true here too. Notice when this asks me, what kind of candy bars do you have? Snickers, enter the number, X, right? Which is not a number. It immediately gives me an error. And let's look at this error. It tells what line the error was on, line 5 right here. And it says on this line, I have a value error, invalid literal for int with base 10 X. So I typed in an X and then I sent that to this int thing that's going to try to convert it into an integer. And it says, I can't do that. And so we get an error. Now notice here we're turning the number of candy bars in a package into an integer. That makes sense, right? Because that is a number. And presumably we're not going to get a bag of candy bars that has, 12.6 candy bars in it, unless there was a packaging error, right? And so it makes sense for that to be an integer. On the other hand, candy bars often weigh not an even number of ounces. And so for the weight, I say, enter the weight in ounces for the candy bar, and I wrap that into a float. And float takes the number, takes whatever I type in and turns it into a float, if it's possible. Now, if I try to change college to a quote, float, of course I get an error, but I can change what they're going to type in is something like 4.2, and it turns it into a float. And so what we're doing here is we're asking 3 questions of the user of this program. What's the name of the candy bar? And we're putting in that into this thing, this box, this place where we can store things, and it's called a variable. We're putting the name into there. Here, we're putting the integer number of bars in a bag in here, candy bar, and here we're putting the weight of each candy bar into this weight candy bar, and we're putting that, we're getting that as a float. Then we get the total weight as the product of the weight of each candy bar and the number of candy bars, and then I print out some stuff. I print out how many candy bars I have. Num candy bar prints out a number. Name candy bar prints out the name and bars. And then I print out the total weight. I'm sorry, I print out how many ounces the candy bars for each candy bar, and then I print out the total weight, which is computed. Now, so let's run this again, actually. How many bars do we have? We have Kenyan bars. Enter the number of bars. So let's say we have 20. Enter the weights in ounces, 5.4. And so we see it all works. Now, every variable in Python has a type, and we've been seeing that, right? In fact, I can look at this. Type num candy bar, and that's an integer. Type name candy bar. I thought I could cut and paste the name candy bar. Oops. Is a string, right? What's the type of the weight of the candy bar going to be? What's the type of that variable?
Float.
That's going to be a float, right? Now, the thing about Python, and this is really kind of interesting, and not all languages are like this. In fact, we're going to see something completely different later when we study C++. In Python, variables are dynamically typed. In other words, they're automatically assigned their type when we declare them or when we put something into them. So if I say down here, x is equal to 3, the type of x is an integer. But then if I go ahead and say x is equal to 4.5, oops, I typed it. X is equal to 4.5, and I look at the type of x again, now it's a float. And then if I say the type of x is equal to hello, and it's a string. So type is determined every time you do an assignment. The type changes. Now, a variable always at any given moment has a specific type, but it can change whenever we assign a new value. And we call that dynamic typing. It turns out in some languages, many languages, you set the type of a variable and it never changes. But in Python, they can change all the time, which frankly, from a software engineering standpoint, in other words, when people talk about computer science and doing things well versus not so well, dynamically typed languages are oftentimes maligned because it's harder to read the code because you can't just look at the code and tell what a particular type it is without doing a lot of investigation. And so some people would say that it's easier to make mistakes in code that is dynamically typed, but it's also really easy to write programs because you can just use a variable anytime, any way you want. So it's a trade-off, right? And so can't really say whether it's better or not that it's that way. You can make lots of arguments, it turns out, in either way. So let's talk about, based on the type then, look at total weight. What is the type of total weight going to be?
Float.
A float. Now, what made you decide it was going to be a float?
Since ounces is also a float, it would make sense that the weight wouldn't be a perfect number either.
Right, so the weight is a float, right. Now it turns out that the weight is a float and the number of the candy bar is an int. So I'm taking a float and an int, and let's just check. Sure enough, it's a float. Let's look at this for a second. If I say x is equal to 1 plus 1, yeah.
Can I ask something? Isn't there a possibility that it still might be an integer? Because
Yeah, okay, so let's see. Let's try something here. I think I know where you're going with this, so let's try this. This is the Kenyan bar. Number of candy bars, 12. Total weight in ounces. What if we say 3? So it's a 3-ounce bar. Now let's do the type. Let's do the type of the total weight. Think it's going to be float or int? Turns out it's still float. Okay, and so let me show you something that might help decode this.
decimal in it?
Say that again.
Is it because of the decimal in it?
Well, right. We see that we do see in the output that there was a decimal there. I'm sorry, here. So we kind of knew it was going to be a float, but what made it a float? Well, let's try something here. If I say x is equal to 1 plus 2, type x, it's an int. If I say int is equal to 1 plus 2.1, it's a float. If I say it's equal to 1.1 times 2.1, it's a float. Now, what if I do this? 2.0 and 1. Well, I gotta find my thing, type X. It's a float. So let's think about what's going on here. It turns out if you add two integers together, or it turns out any operations, if you do an operation of two integers and it's always going to be an integer. If it's an integer and a float, because the float has more precision, the result always gets upgraded to the more precise thing, which is the float. Okay? And so Python is going to try to pick the type that's going to lose the least amount of information in general, is one way to think about it. Now, when we do operations in Python, one of the things that matters is compatibility of types. For example, I can make a 1 plus a 2, and I get a 3, right? If I say 1 plus 3.4, of course, I get 4.4. If I do 1 plus, quote, 4, what's going to happen? Well, it turns out I get an error because it says type error, unsupported operand types. It turns out that plus doesn't allow you to add a number to a string because it doesn't make any sense, because I could have just as easily done this. Right? So you can't add numbers and strings. Doesn't make sense. And then, by the way, so now what about 3 times 3? Of course, that's 9. What about 3 times Kenyon? Now, we saw this before. Kenyon, Kenyon, Kenyon. In fact, I could do 30 times Kenyon. Get a lot of them. Really want to be crazy. 300 Kenyons. So it turns out that plus will not add a number and a 300 times 4, of course, is 1200. Plus is only defined between 2 numbers, float or integer, or 2 strings. It turns out we can add strings, but we can't add them like numbers. Like I can do Kenyon, whoops, Kenyon plus college and get Kenyon college. So it turns out adding works with strings, but it does something called concatenation. It turns out that adding works with numbers, but it does adding. Now we can't add a string and a number because that doesn't make sense. But what about, but we saw that we could multiply a number times a string and get that string repeated that many times. So there's some interesting nuances here that you guys will get used to. I mean, does that raise any questions? Is anybody troubled by all of this?
Can we multiply a string with a float?
Can I multiply a string with a float? Oh, yes. Very good question. Excellent question. Kenyon times 2.5. Huh. No. Turns out that you can only repeat a string an integer number of times.
Also, how could you get a space in between Kenyon College?
So let's go up and look at that. What we could do is do plus space plus Kenyon, right? A space, a string, quotes around a space is a string. So we can add together lots of strings. Now, what if I do this and then I do times 3, 4? Now, what happened there?
It only multiplied against the last string.
Right. Now, this has something to do with something called operator precedence that we're going to learn about a little more later. But it turns out that if you have to, that pluses, that times have a higher precedence, which means you do multiplies before you do adds. And so it does the multiply first, and it says 4 times college, and then it adds Kenyon to it. Now notice I can change that with parentheses, just like I can in mathematics. If I put parentheses around Kenyon plus space plus college, I get Kenyon college, Kenyon college, Kenyon college. In fact, I could do this, plus, quote, and no, I did the wrong slash. No, wait. Now I'm confused. Not sure why that didn't work. That's kind of a surprise, isn't it, Sejin? Does that surprise you too? Actually, I think. Well, I don't want to dwell on that for right now. So we've got this code and it did some stuff, and hopefully you guys are learning it. Now let's try something new here. I'm going to give you guys a couple of minutes to try this on your own. Add a new variable called calories per bar. Think about what type that should be, and add an input asking for the user to enter the number of calories per bar, and then add a statement to compute and output the total number of calories in the bag of bars. So see if you can do that. Let me give you a couple of minutes on yours.
Can you please re-explain what we have to do?
Okay, so it's in the comments here. It says, add a new variable called calories per bars. And you need to think about what type that's going to be. And then add an input prompt that asks for the number of calories and it puts it in that variable. So you're going to need to decide if it's an integer or a float or a string. And then add a statement that computes the total calories. In other words, it's going to multiply these calories per bar times the number of bars, and then print out the total number of calories in all the bars. So see if you can do that. And normally at this point, Sajid and I would be walking around campus looking over your shoulders, but we can't do that. But if you have questions you need to ask, you can either ask publicly or privately on the chat or verbally. Okay. How do we fill in this calories per bar? What would we do here? Anybody?
Well, we need to have an input.
Right. So we're going to input into calories per bar, right?
Mm-hmm.
So what type is it going to be?
I think we want it as a float.
Okay, let's try that. Like
Sorry, FL, yeah.
Yeah, I can't type for some reason. Yeah.
And then you do input and in parentheses, how many calories per bar. I guess for an example.
Okay, so that should get us our calories.
And if we then want to have it actually posted or printed, we'd use the print command. And I guess we could call it, do we want to do total calories? Yeah, that works. And then candy bar times calories per bar. Oh, sorry, we need total calories, but we need a comma. Or you have that, okay.
Well, we haven't computed the total calories. We either have to compute it ahead. So we can do this all at once, right? We can say calories per bar
Mm-hmm. Times
times,
number of calories, yeah. Number of bars, I guess.
number of candy bar, right?
Mm-hmm.
And so what that should do is compute the total number of calories by multiplying the calories per bar. So we can try this now. We test it. And that's one of the things we do is write your programs a little bit of time and then test them. So we still got to do this. Kenyon, enter the number of candy bars, 15, total weight, 5.3, calories per bar. Let's say it's 110 calories per bar. And so this is 1,650. And what's the type of that answer?
The type is currently in a float because it has a 0.0, right? It has a decimal.
Right, yeah.
Could we, I mean, is it better to do it in integer for this one?
Well, you could. I wouldn't, that's a good question. The truth is I've never seen packaging, but I could be wrong. This is anecdotal. I've never seen packaging that gives the number of calories as a decimal, right? It's always as an integer.
Yeah.
So I think you could go either way. I don't think it's bad to leave it as a float, but I think it's open for opinion there. So, and what I think may not be the only thing. So now let's try something else. Assume that the typical candy bar weighs 1.7 ounces. That coded to display the number of bytes per bar and then the total number of bytes for all the bars. Huh. Now we have to think about this one a little bit, because if somebody's eating a bar, let's say if the bar is 1.4 ounces, then it's going to take exactly 2 bytes. But what if the bar is 1.6 ounces? See, because what I'm asking you to do is first compute the number of bytes per bar, then compute the total number of bytes per bag. And we're going to assume that we eat 1 bar at a time. I hope that's what people do, unless they're real gluttons. And somehow line the bars all up so they can always take a 0.7 ounce bite by biting into multiple bars. But how do I compute the number of bytes for 1 bar? Let's see. So we could make a variable bytes per bar. And what's that going to be equal to? I said bits per bar. Any ideas? Well, before we do that, let's think of the general algorithm. Okay. So let's say the bars are 0.4. It's a very small bar. It's a 0.7 ounce bar. How many bytes is that going to be?
1.
What if the bar is 1.2 ounces?
2.
It's going to be 2 because it's going to be a 0.7 and then the 0.5 that's left, right? What if it's 3.2?
6.
Right.
Or 5.
So if we take 3.2 divided by 0.7, we see that it is 4.5, but we're calling a byte, right? So it's 4.5, we're going to call 5. So we need to find a way. We can do this division to get the exact number of bytes, but we need to round up, don't we? Huh. Any ideas how to do that?
I looked at
Yeah, what'd you find?
math.
I'm sorry. Yeah, go ahead.
A math set of functions, and then
So that's something we're going to learn
Can you read?
soon, but good job. there's some math functions that give us abilities. And what is the function you found?
I found ceiling.
Ah,
And so
ceiling.
by doing
ceiling is
math dot
right. Ceiling is a math function that takes a float and makes it to the next higher integer, right? Now, in order to get to that, we had to do something at the beginning of the program, didn't we? We have to do, now we'll explain this later, but import math import. Okay, this allows us to bring in some special functions. And then once I've imported math, I can do math functions. So what I could do to start with is we can see that basically what we want here is the, let's see what it is, weight of the candy bar divided by 0.7. And then we want to take the ceiling of that. So it turns out we can say math dot ceiling, which is kind of like the int function or the float function. I don't think I did. Oh, I have to spell this correctly. So what this is doing is it's saying, hey, there's some special things in math. Again, we're going to learn more about this later. Let's take a number and find the next higher number, and then I can print out bytes per bar. Oops, I don't know what I just did, per bar. Comma bytes per bar. Let's see if that works. We run it. What kind of candy bar do we have? We have Kenyan bars. Oh, I have to have my focus in the right screen. Kenyan, 35 bars. This is a big bag, or big bars too, 6.4 ounces. How many calories per bar? Well, those are going to be a lot. So we're going to say 160 calories per bar.
It's not math ceiling, it's math seal with no ing.
Aha, thank you. So let's try it again. What kind of bars do you want? Kenyan, 23. How many calories? 140. And there we go, 8 bytes per bar, right? So that was a little trick. We're kind of jumping ahead and learning this, and I'm showing you this, but ceil is a function, and there's a lot of functions that allow us to take a value and do something to it. Now, if we wanted to print bytes per bag, what would that be? It's going to be bytes per bar, right, times the number of bars. Candy bar. Oops. There we go. So we can try this now. And again, this is what you should do. You should test your programs a lot, right? One of the things you're going to be reading is the debug thing for next time. And one of the things you do is you build your programs a little bit at a time, and then you try them out. What kind of candy bars do you have? Kenyan, 10, weight, 5.2. How many calories? 180 bytes per bag. Huh. Oh yeah, eight bytes per bar, 80 bytes per bag. So, any questions on that? So what we're doing is we're kind of learning how to use REPL. We're kind of learning how to do some simple stuff. we are learning how to write a program a little bit at a time. So let's see what's next. A person burns their weight times 0.7 calories per mile walking, and their weight times 0.72 calories per mile running. Ask the person for their weight. Tell them how many miles they would need to run or walk to burn off one candy bar, and how many to burn off the entire candy bar. So that makes me think I probably better go up here and actually have a calories per bag, which I didn't do. I just did the computation on the fly. So let's take this and actually do a calculation. Calories per bag is calories per bar times candy per bar, number of candy per bar. And so now I have two variables, calories per bar and calories per bag. So clearly what I need to do is add somebody for their weight, right? So I could have weight is equal to, now what kind of a value do you think weight should be?
Well,
Okay, we could do a float, we could do an integer, probably either would be fine. Most people don't compute their weight in tenths, but maybe if you're on some special diet, you might. Float input, what is your weight in pounds? And we're assuming this is pounds here. All right. So walking, how many calories are they going to burn per mile walking? How many calories? Actually, maybe I'll call this per mile walking. What is it going to be? Look, it's going to be their weight times 0.57, right? And we could do this. I can actually take and copy and paste this, speed things up. Mile per mile running might as well just retyped it. I had to make enough edits to it. Per mile is going to be 0.72. So we could actually write that out. Print, you burn, better put quotes in here. Per mile walking. Oops, I didn't put a comma in here. Per mile walking for each mile walked. And I could take and copy that line. You burn per miles running. Oops. For each mile ran. Well, let's see what happens. Let's look at this, see if this works. How many candy bars? We got 450 candy bars. They weigh 570, number, oh, that's the name of it. 567 candy bars. The weight of each candy bar is 34 ounces. So these are really big candy bars. How many calories per bar? Well, that's going to be a lot. 1,200 calories per bar. And what is your weight in pounds? Now my weight is 185, so I'll type that in. And so I burn 105 for each mile walked and 133 for each mile that I ran. I don't know if I should say ran or run there. I think it sounds better with a run. Okay. So how do I compute the number of calories? I mean, okay. How many miles would I need to walk to burn off the bar? What do I need to do? Any ideas? Anyone? You guys are quiet. Have I lost you or are you guys still there?
You can divide the calories per bar by the per mile walking or per mile running.
Okay, so we say walk miles is equal to, say that again. Take and do what?
You take the calories per bar and divide it by your value for per mile walking.
Okay, that's how many miles I have to walk. Now I can take this equation and copy it again and do run miles, calories per bar per calorie running, right? So now I should be able to print out the solution. Print you must walk. Oh, it helps if I put quotes around things. You must walk miles to burn off 1 bar of, just for fun, I'll put the name of it in. I don't remember the name of them. Okay, what are they? Name candy bar. Right? 1 burb. 1 bar. You must, to burn off, sorry. To burn off. Again, I forgot my quotes. So you must walk Bach miles to burn off 1 bar of, and then we can do this again. So we're going to tell how many miles they have to walk. You must run miles to burn off 1 bar of. So let's try this. Okay, we'll try it out. What kind of candy bars? Kenyan. Number of candy bars, 12, which isn't going to make a big deal. The number of the weight is 3.1, let's say. How many calories per bar? Let's say 160. So that's a total calorie. Okay. What is your weight in pounds? Let's say we're 190. You burn 108, 136. Okay, so you must walk 1.4 miles to burn off, I should have said miles there, and you must run 1.1 miles. So I should go over here. And so this is kind of how we program, right? We see problems and we fix them. So that's it. Now I want you need to do it for the whole bag. I'll let you think about how to do the whole bag. and then write out a message as a sentence explaining how much exercise must be done to use up the calories of the candy bars, and encourage the user to eat something healthier and include the name of the candy bars in the output. So go ahead and finish this, and then you turn it in on, and what do you turn in on Moodle? You just take the link, the entire link, copy that, and paste it into Moodle, okay? And then I can look at your code. Any questions at this point?
I did have a question. Could you explain seal? I didn't 100% get what seal did.
What did, oh, the seal, okay.
Yeah.
That's a good question, and that probably confused quite a few people, and I wasn't expecting that. Somebody brought it in, so I went ahead and went with it. Seal, in mathematics, there's two functions, the ceiling function and the floor function, and math.seal takes a floating point number and rounds it up to the next closest integer. And it turns out that even if it's a very small thing, it goes up. Now, if it happens to just be 5, then it stays at 5. But if it's anything above higher than 5, it goes to the next one, right? So this could be any number, 7, right? So that's ceiling. It takes it up to the ceiling of that. Now, it turns out that there's another one called floor, which basically is kind of like taking the int of a float. It just takes you down. So that turned out to be quite useful. Now, there's other ways we could do it, but that was probably the simplest way. So thank you. And we're going to be learning lots and lots of other ways. Now, the truth is I don't really expect you, I'm sort of giving you extra to talking about the ceiling, because that's something we were going to get later anyway, but we didn't need it now. But good question anyway. It's never too soon to learn things. Now again, and I am, by the way, if some of you guys need to see this again, you're a glutton for punishment, I am going to be posting this link on the wiki for the video of this class after class. It'll take probably take a half an hour to well, I'll have to take an hour or two to get it rendered and compressed and uploaded and a link in. But when it's done, I will give that to you. Anybody else have a question?
The notes that you showed us in the starting, can we get those notes as well?
I'm going to need you to say that again.
I'm saying that the notes that you showed us in the start, the PowerPoint presentation.
Yeah, okay, yeah, those are right here. Let me show you. PowerPoints are, here's the wiki page right here, right? Is that what you're seeing? And so for every class, if I ever have slides, the slides are going to be here, and so is the video. So here is the slides for today. So anytime I show slides in class, they will be available on the web page.
I have a question about like the repo 1.1 through 1.4. So what is that?
Okay, yeah, we didn't get that today, but I wasn't sure if we would or not, and I decided not to because I didn't in the first class either. But I put that there just in case we ran out of time. I'm going to be doing that. I'll be doing that on the 15th, and that's going to, what I'm going to do is show you how you solve problems. I got 1 minute, so I can at least kind of introduce that to you. If you go into the class, actually, I'm not a student in the class, so well, I guess I am. Let me see. Okay, so if you go, no, that's not the right one. Okay, so I'll have to go in as teacher. Okay, so if you go into, if you correctly signed up for the REPL class, you can go in and you will see a bunch of problems, okay? Now, I haven't actually published those problems, and I'll do that after class today, but what you'll see is things like this. And I'll actually have this done by the end of today so you can start to go in and see them. Now, problem 1.1, this is a problem. And what it says is this program reads two numbers and prints their sum. Okay. Now, so this gives you some code to start with. And then here's the problem statement. Write a program that takes three numbers and prints their sum. So what I do is modify this. Yeah, go ahead.
We can't see your screen. I don't think you're sharing your screen right now.
Oh, I thought I was. Okay. Well, that's annoying. Okay, so let me, we're out of time, and you don't need to know this yet, so I'm actually not going to show you right now anyway, because I'm not really ready. We're going to look at this on Tuesday. We don't need to know it before then. So enjoy your weekend, and thank you for coming to class. See you later.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.
I'll be in office hours now, by the way, if anybody needs help.
Thank you.
Professor, I do have a quick question. Also,
Yeah.
like regarding homework.
Yeah.
So, what do you want us to do with the chapter 2.13, like
Right.
from
So what
the
you're
Python?
supposed to do is take the code that you write for there and go into Moodle, and there's a Python. I can actually show this to you. Okay, are you seeing Moodle now?
Yeah.
Okay, so you go in here, candy bar, no, that's the other thing, sorry. You go into Python 2.3 exercises, and then what you're going to do, now you're seeing the teacher view, but when you go in there, there's a text box that you can submit stuff in. So what you do is you paste all your code into that text box and hit submit. That's all you have to do.
Oh, okay, cool. So for this one, you want us to copy and paste our code, whereas for
right. So I have a copy of it.
Okay, but for the candy bar, you just want the link so that you can just click on that.
Candy bar, I just want the link. Yeah.
Okay.
And the 2.13 exercises, are they due tonight or next class?
Let's go see. Good question. I got to remember. Those, I believe, are due. Well, let's look over here. Those are due on midnight on the 15th.
Okay. Thank you.
Okay.
Yeah.
All right. Take care.
Thank you. Bye.
Bye-bye.